Structural steel is a category of steel used for making construction materials in a variety of shapes. Many structural steel shapes take the form of an elongated beam having a profile of a specific cross-section. Structural steel shapes, sizes, chemical composition, mechanical properties such as strength, storage practices, etc., are regulated by standards in most industrialized countries. Most structural steel shapes, such as I-beams, have high second moments of area, which means they are very stiff in respect to their cross-sectional area and thus can support a high load without excessive sagging. Common structural shapes. The shapes available are described in many published standards worldwide, and a number of specialist and proprietary cross-sections are also available. I-beam, I-shaped cross-section. In Britain these include universal beams, UB, and universal columns, UC. In Europe it includes the IPE, HE, HL, HD and other sections. In the US it includes wide flange, WF, a W-shape, and H sections, Z-shape, half a flange in opposite directions, HSS shape, hollow structural section also known as SHS, structural hollow section, and including square, rectangular, circular, pipe, and elliptical cross-sections, angle, L-shaped cross-section, structural channel, or C-beam, or C-cross-section, T-shaped cross-section, rail profile, asymmetrical I-beam, railway rail, vignettes rail, flanged T-rail, grooved rail, bar, a piece of metal, rectangular cross-sectioned, flat, and long, but not so wide so as to be called a sheet, rod, around a square and long piece of metal. See also rebar and dowel, plate, metal sheets thicker than 6 mm or 1/4 in, open web steel joist. While many sections are made by hot or cold rolling, others are made by welding together flat or bend plates. For example, the largest circular hollow sections are made from flat plate bent into a circle and seam welded. The terms angle iron, channel iron, and sheet iron have been in common use since before wrought iron was replaced by steel for commercial purposes. They have lived on after the era of commercial wrought iron and are still sometimes heard today. Informally, in reference to steel angle stock, channel stock, and sheet, despite that they are misnomers. Compare tin foil, still sometimes used informally for aluminum foil. Informal writing for metalworking contexts. Accurate terms like angle stock, channel stock, and sheet are used. Standards. Standard structural steels. Europe. Most steels used throughout Europe are specified to comply with the European standard EN 10025. However, many national standards also remain in force. Typical grades are described as S275J2 or S355K2W. In these examples, S denotes structural rather than engineering steel. 275 or 355 denotes the yield strength in newtons per square millimeter or the equivalent megapascals. J2 or K2 denotes the material's toughness by reference to Sharpe impact test values, and the W denotes weathering steel. Further letters can be used to designate fine-grained steel, and or Ni, quenched and tempered steel, Q or QL, and thermomechanically rolled steel, M or ML. 1. S275JOH specification. S275JOH is steel grade in EN 10219 specification, EN 10210 standard, and the most widely used specification is EN 10219 standard, which is cold-formed welded structural hollow sections of non-alloy and fine-grained steels. EN 10219-1 specifies the technical delivery conditions for cold-formed welded structural hollow sections of circular, square or rectangular forms and applies to structural hollow sections formed cold without subsequent heat treatment. Requirements for S275JOH pipe tolerances. Dimensions in sectional S275 pipe properties are contained in N 10219-2. 2. S275JOH steel pipes manufacture process. The steel manufacturing process shall be at the discretion of the steel producer. S275JOH carbon steel pipes can be made in Eru SAW a seamless process. All S275JOH steel material and S275JOH pipes should conform to EN 10219 standards. The normal yield strength grades available are 195, 235, 275, 355, 420, and 460. Although some grades are more commonly used than others e.g. in the UK, almost all structural steel is grades S275 and S355. Higher grades are available in quenched and tempered material. 500, 550, 620, 690, 890 and 960, although grades above 690 receive little if any use in construction at present. A set of Euronorms define the shape of a set of standard structural profiles. European I-beam, IP, Euronorm 19-57. European I-beam, IPN, DIN 1025-1. European flange beams, HE, Euronorm 53-62. European channels, UPN, DIN 1026-1. European cold-formed as is 800-1. Standard structural steels, USA. Steels used for building construction in the U.S. use standard alloys identified and specified by ASTM International. These steels have an alloy identification beginning with A and then 2, 3, or 4 numbers. The 4-number AISI steel grades commonly used for mechanical engineering machines and vehicles are a completely different specification series. The standard commonly used structural steels are carbon steels A36 structural shapes and plate, A53 structural pipe and tubing, A500 structural pipe and tubing, A501 structural pipe and tubing, A529 structural shapes and plate, high strength low alloy steels A441 structural shapes and plates, A572 structural shapes and plates, A618 structural pipe and tubing, A992 possible applications are W or SI beams, A913 quenched and self-tempered, QST, W shapes, A270 structural shapes and plates, A521 structural plates and shapes infinity, corrosion-resistant high-strength low-alloy steels A243 structural shapes and plates, A588 structural shapes and plates, quenched and tempered alloy steels A514 structural shapes and plates, A517 boilers and pressure vessels, Eglin steel, inexpensive aerospace and weaponry items. CE marking. The concept of CE marking for all construction products and steel products is introduced by the Construction Products Directive, CPD. The CPD is a European directive that ensures the free movement of all construction products within the European Union. Because steel components are safety critical, CE marking is not allowed unless the Factory Production Control (FPC) system under which they are produced has been assessed by a suitable certification body that has been approved to the European Commission. In the case of steel products such as sections, bolts and fabricated steelwork, the CE marking demonstrates that the product complies with the relevant harmonized standard. For steel structures, the main harmonized standards are steel sections and plate, N10025-1. Hollow sections, N10219-1 and N10210-1. Preloadable bolts, N14399-1. Non-preloadable bolts, N15048-1. Fabricated steel, N1090-1. The standard that covers CE marking of structural steelwork is N1090-1. The standard has come into force in late 2010. After a transmission period of 2 years, CE marking will become mandatory in most European countries sometime early in 2012. The official end date of the transition period is July 1, 2014. Steel versus concrete. Choosing the ideal structural material. Most construction projects require the use of hundreds of different materials. These range from concrete of all different specifications, structural steel of different specifications, clay, mortar, ceramics, wood, etc. In terms of a load-bearing structural frame, they will generally consist of structural steel, concrete, masonry, and/or wood, using a suitable combination of each to produce an efficient structure. Most commercial and industrial structures are primarily constructed using either structural steel or reinforced concrete. When designing a structure, an engineer must decide which, if not both, material is most suitable for the design. There are many factors considered when choosing a construction material. Cost is commonly the controlling element. However, other considerations such as weight, strength, constructability, availability, sustainability, and fire resistance will be taken into account before a final decision is made. Cost. The cost of these construction materials will depend entirely on the geographical location of the project and the availability of the materials. Just as the price of gasoline fluctuates, so do the prices of cement, aggregate, steel, etc. Reinforced concrete derives about half of its construction costs from the required formwork. This refers to the lumber necessary to build the box or container in which the concrete is poured and held until it cures. The expense of the forms makes precast concrete a popular option for designers due to the reduced costs and time. Due to the fact that steel is sold by weight, it is the responsibility of the structural designer to specify the lightest members possible while still maintaining a safe structural design. An additional method of reducing expenditures in design is to use many of the same size steel members as opposed to many unique members. Strength, weight ratio. Construction materials are commonly categorized by their strength to weight ratio, or specific strength. This is defined as the strength of a material over its density. This gives an engineer an indication as to how useful the material is in comparison to its weight, with the weight being a direct indication of its cost, typically, and ease of construction. Concrete is typically 10 times stronger in compression than in tension, giving it a higher strength to weight ratio in compression only. Sustainability. Many construction companies and material vendors are making changes to be a more environmentally friendly company. Sustainability has become an entirely new consideration for materials that are to be placed into the environment for generations of time. A sustainable material will be one that has minimal effect on the environment, both at the time of installation as well as throughout the life cycle of the material. Reinforced concrete and structural steel both have the ability to be a sustainable construction option, if used properly. Over 80% of structural steel members fabricated today come from recycled metals, called A992 steel. This member material is cheaper, as well as having a higher strength-to-weight ratio than previously used steel members. A36 grade reinforced concrete can also be a very sustainable option. Concrete's material components are naturally occurring materials that are not harmful to the environment. Also, concrete can now be poured to be permeable, allowing the flow of water through a paved surface and therefore reducing the necessary infrastructural construction that causes further potential disturbance to the environment. Concrete can also be crushed and used as aggregate in future concrete applications, meaning it doesn't necessarily have to be used as a landfill. Fire resistance. One of the most dangerous hazards to a building is a fire hazard. This is especially true in dry, windy climates and for structures constructed using wood. Special considerations must be taken into account with structural steel to ensure it is not under a dangerous fire hazard condition. Reinforced concrete characteristically does not pose a threat in the event of fire and even resists the spreading of fire, as well as temperature changes. This makes concrete an excellent insulation, improving the sustainability of the building it surrounds by reducing the required energy to maintain climate corrosion. When choosing a structural material, it is important to consider the life cycle of the building. Some materials are susceptible to corrosion from their surrounding elements, such as water, heat, humidity, or salt. Special considerations must be taken into account during the installation of a structural material to prevent any potential corrosion hazards. This must also be made clear to the occupants of the building because there may or may not be a necessary maintenance requirement to prevent corrosion. For example, structural steel cannot be exposed to the environment because any moisture or other contact with water will cause it to rust. When the steel rusts, it compromises the structural integrity of the building and poses a potential danger to the residual or surrounding occupants. Reinforced concrete characteristics, generally consisting of Portland cement, water, construction aggregate, coarse and fine, and steel reinforcing bars, rebar. Concrete is cheaper in comparison to structural steel. Strength. Concrete is a composite material with relatively high compressive strength properties, but lacking in tensile strength, ductility. This inherently makes concrete a useful material for carrying the weight of a structure. Concrete reinforced with steel rebar give the structure a stronger tensile capacity, as well as an increase in ductility and elasticity. Constructability. Reinforced concrete must be poured and left to set, or harden, after setting, typically 1 to 2 days. A concrete must cure, the process in which concrete experiences a chemical reaction between the cementitious particles and the water. The curing process is complete after 28 days. However, construction may continue after 1 to 2 weeks. Depending on the nature of the structure, concrete can be constructed into nearly any shape and size. Approximately half of the cost of using reinforced concrete in a structural project is attributed to the construction of the formwork. In order to save time, and therefore costs, structural concrete members may be precast. This refers to a reinforced concrete beam, girder, or column being pulled off-site and left to cure. After the curing process, the concrete member may be delivered to the construction site and installed as soon as it is needed. Since the concrete member was cured off location beforehand, construction may continue immediately after erection. Fire resistance. Concrete has excellent fire resistance properties, requiring no additional construction costs to adhere to the International Building Code (IBC) fire protection standards. However, concrete buildings will still likely use other materials that are not fire resistant. Therefore, a designer must still take into account the use of the concrete and where it will require fire hazardous materials in order to prevent future complications in the overall design. Corrosion. Reinforced concrete, when constructed properly, has excellent corrosion resistance properties. Concrete is not only resistant to water, but needs it to cure and develop its strength over time. However, the steel reinforcement in the concrete must not be exposed in order to prevent its corrosion, as this could significantly reduce the ultimate strength of the structure. The American Concrete Institute provides the necessary design specifications for an engineer to ensure there is enough concrete covering any steel reinforcement to prevent exposure to water. This cover distance must be specified because concrete will inevitably crack at locations carrying tension, or locations containing reinforcing bars for the purpose of carrying said tension. If the concrete cracks, it provides a path for water to travel directly to the reinforcing bars. Some reinforcing bars are coated in epoxy as a second-order measure of preventing corrosion due to water contact. This method induces higher costs on the overall project. However, due to the higher cost of the epoxy-coated bars, also, when using epoxy-coated bars, reinforced concrete members must be designed larger, as well as stronger, in order to balance the loss of friction between the reinforcing bars and concrete. This friction is referred to as bond strength, and it is vital to the structural integrity of a concrete member. Structural steel. Characteristics. Structural steel differs from concrete in its attributed compressive strength as well as tensile strength. Strength, having high strength, stiffness, toughness, and ductile properties. Structural steel is one of the most commonly used materials in commercial and industrial building construction. Constructability. Structural steel can be developed into nearly any shape, which are either bolted or welded together in construction. Structural steel can be erected as soon as the materials are delivered on site, whereas concrete must be cured at least 1 to 2 weeks after pouring before construction can continue, making steel a schedule-friendly construction material. Fire resistance. Steel is inherently a non-combustible material. However, when heated to temperatures seen in a fire scenario, the strength and stiffness of the material is significantly reduced. The International Building Code requires steel be enveloped in sufficient fire-resistant materials, increasing overall cost of steel structure buildings. Corrosion. Steel, when in contact with water, can corrode, creating a potentially dangerous structure. Measures must be taken in structural steel construction to prevent any lifetime corrosion. The steel can be painted, providing water resistance. Also, the fire resistance material used to envelope steel is commonly water resistant. Mold. Steel provides a less suitable surface environment for mold to grow than wood. The tallest structures today, commonly called skyscrapers or high-rise, are constructed using structural steel due to its constructability, as well as its high strength-to-weight ratio. In comparison, concrete, while being less dense than steel, has a much lower strength-to-weight ratio. This is due to the much larger volume required for a structural concrete member to support the same load. Steel, though denser, does not require as much material to carry a load. However, this advantage becomes insignificant for low-rise buildings, or those with several stories or less. Low-rise buildings distribute much smaller loads than high-rise structures, making concrete the economical choice. This is especially true for simple structures, such as parking garages, or any building that is a simple, rectilinear shape. Structural steel and reinforced concrete are not always chosen solely because they are the most ideal material for the structure. Companies rely on the ability to turn a profit for any construction project. As do the designers. The price of raw materials, steel, cement, coarse aggregate, fine aggregate, lumber for formwork, etc., is constantly changing. If a structure could be constructed using either material, the cheapest of the two will likely control. Another significant variable is the location of the project. The closest steel fabrication facility may be much further from the construction site than the nearest concrete supplier. The high cost of energy and transportation will control the selection of the material as well. All of these costs will be taken into consideration before the conceptual design of a construction project is begun. Combining steel and reinforced concrete structures consisting of both materials utilize the benefits of structural steel and reinforced concrete. This is already common practice in reinforced concrete in that the steel reinforcement is used to provide steel's tensile strength capacity to a structural concrete member. A commonly seen example would be parking garages. Some parking garages are constructed using structural steel columns and reinforced concrete slabs. The concrete will be poured for the foundational footings, giving the parking garage a surface to be built on. The steel columns will be connected to the slab by bolting and/or welding them to steel studs, extruding from the surface of the poured concrete slab. Precast concrete beams may be delivered on site to be installed for the second floor, after which a concrete slab may be poured for the pavement area. This can be done for multiple stories. A parking garage of this type is just one possible example of many structures that may use both reinforced concrete and structural steel. A structural engineer understands that there are an infinite number of designs that will produce an efficient, safe, and affordable building. It is the engineer's job to work alongside the owner, contractor, and all other parties involved to produce an ideal product that suits everyone's needs. When choosing the structural materials for their structure, the engineer has many variables to consider, such as the cost, strength, weight ratio, sustainability of the material, constructability, etc. Thermal properties. The properties of steel vary widely, depending on its alloying elements. The austenizing temperature. The temperature where a steel transforms to an austenite crystal structure. For steel starts at 900 degrees Celsius, 1650 degrees Fahrenheit. For pure iron, then, as more carbon is added, the temperature falls to a minimum 724 degrees Celsius, 1335 degrees Fahrenheit. For eutectic steel, steel with only 83% by weight of carbon in it, as 2.1% carbon by mass is approached, the austenizing temperature climbs back up to 1130 degrees Celsius, 2070 degrees Fahrenheit. Similarly, the melting point of steel changes based on the alloy. The lowest temperature at which a plain carbon steel can begin to melt, its solidus, is 1130 degrees Celsius, 2070 degrees Fahrenheit. Steel never turns into a liquid below this temperature. Pure iron, steel with 0% carbon, starts to melt at 1492 degrees Celsius, 2718 degrees Fahrenheit, and is completely liquid upon reaching 1539 degrees Celsius, 2,802 degrees Fahrenheit. Steel with 2.1% carbon by weight begins melting at 1,130 degrees Celsius, 2,070 degrees Fahrenheit, and is completely molten upon reaching 1,315 degrees Celsius, 2,399 degrees Fahrenheit. Steel with more than 2.1% carbon is no longer steel, but is known as cast iron. Fire resistance. Steel loses strength when heated sufficiently. The critical temperature of a steel member is the temperature at which it cannot safely support its load. Building codes and structural engineering standard practice defines different critical temperatures depending on the structural element type, configuration, orientation, and loading characteristics. The critical temperature is often considered the temperature at which its yield stress has been reduced to 60% of the room temperature yield stress. In order to determine the fire resistance rating of a steel member, accepted calculations practice can be used, or a fire test can be performed, the critical temperature of which is set by the standard accepted to the authority having jurisdiction, such as a building code. In Japan, this is below 400 degrees Celsius. In China, Europe and North America, e.g., ASTM E119, this is approximately 1000 to 1300 degrees Fahrenheit, 530 to 810 degrees Celsius. The time it takes for the steel element that is being tested to reach the temperature set by the test standard determines the duration of the fire resistance rating. Heat transfer to the steel can be slowed by the use of fireproofing materials, thus limiting steel temperature. Common fireproofing methods for structural steel include intumescent, endothermic, and plaster coatings, as well as drywall, calcium silicate cladding, and mineral wool insulating blankets. Concrete building structures often meet code-required fire resistance ratings, as the concrete thickness over the steel rebar provides sufficient fire resistance. However, concrete can be subject to spalling, particularly if it has an elevated moisture content. Although additional fireproofing is not often applied to concrete building structures, it is sometimes used in traffic tunnels and locations where a hydrocarbon fuel fire is more likely, as flammable liquid fires provides more heat to the structural element as compared to a fire involving ordinary combustibles during the same fire period. Structural steel fireproofing materials include intumescent, endothermic and plaster coatings, as well as drywall, calcium silicate cladding, and mineral or high-temperature insulation wool blankets. Attention is given to connections, as the thermal expansion of structural elements can compromise fire resistance rated assemblies. Manufacturing. Cutting workpieces to length is usually done with a bandsaw. A beam drill line has long been considered an indispensable way to drill holes and mill slots into beams, channels and HSS elements. CNC beam drill lines are typically equipped with feed conveyors and position sensors to move the element into position for drilling, plus probing capability to determine the precise location where the hole or slot is to be cut. For cutting irregular openings and non-uniform ends on dimensional, non-plate elements, a cutting torch is typically used. Oxy-fuel torches are the most common technology and range from simple handheld torches to automated CNC coping machines that move the torch head around the structural element in accordance with cutting instructions programmed into the machine. Fabricating flat plate is performed on a plate processing center where the plate is laid flat on a stationary table, and different cutting heads traverse the plate from a gantry-style arm or bridge. The cutting heads can include a punch, Drill a torch. See also. Guide to the CE marking of structural steelwork. BCSA Publication No. 46/08. Encyclopedia for Steel Construction Information.